Here's a geometry puzzle by me, problem number 6. 5 points are equally spaced around the circumference of a circle. Bonnie wants to draw a star with these points, but she forgot the order of the points. Instead, she labels them at random with the numbers 1 through 5 in some order and with no repeated numbers. Then she draws the star by drawing the path from 1 to 2 to 3 to 4 to 5, and then back to 1 with 5 straight lines. An example of Bonnie's star is shown below, dividing the circle into 7 regions. Those regions 1, 2, 3, 4, 5, 6, and 7. So you can see there are 7 regions. The expected number of regions Bonnie divides a circle into can be expressed as m over n for relatively prime m and n. Find m plus n. Let's draw a bigger diagram here to see what's going on. So 5 points again. 1, 2, 3, 4, 5, right? Imagine we just label it in order. What will our star look like? Well, it will just be a pentagon, right? 1, 2, 3, 4, 5, back to 1. That will give us this. And we can see that there are 6 regions here. So let's think about how many regions are produced. Well, we start with 1 region, right? And every time we draw a line, we're basically creating more pieces. So for example, if we connected these points first, then we basically divide that into an additional piece so that we get 2 total pieces. And we can connect it to here, so now it's 3 pieces. And we can see that we can repeat this. And we notice that when we do this, the number of pieces always increases like this. And notice that whenever we hit an intersection, we basically generate a new slice. So when we start here, we come here, we hit the edge here, creating a new piece, basically separating these 2 halves here. Then we move along here, separating these 2 halves, creating a new 3rd piece. Then we do this, we hit the original cut here, which creates a new piece. And then finally we hit this, which creates again a new piece. Now then we can finish off by doing this. Notice that we create a new piece every time we intersect the curve, and also if we touch the circle, right? So here we create a new piece, we create another new piece by dividing this central triangle in half. Then we create one final piece, and these 2 regions get divided. And then finally we can do this. We hit this line here, so we create a new region. Here we create a new region, and here we create a new region. So notice that we create a new region every time one of these 2 things happens, right? Either the path self-intersects, or 2, the path hits the circumference, right, of the circle. So really, the number of pieces that we generate can be written as 1 plus, right? Since we start with 1 total piece, the number of times the path self-intersects plus the number of times the path hits the circumference. You can see that the ladder is always 5, right? Particular, we start here, ignoring all the intersections, right? We're just generating these 5 new regions here, right? Basically, every time we draw the line, we're creating a new region containing each of these edges, right? So we have 5 default regions, so that's 6 plus the number of self-intersections. Notice that we can also do this because, well, we have the special case. Imagine we had a regular hexagon instead of a pentagon. We would need to worry about this, for example, this triple intersection, in which case, right, even though, I'll draw an example. If we start here to 1, 2, 3, 4, 5, 6, Notice that, and then we go back to 1. Notice that this creates 1, 2, 3, 4, 5, 6, 7, 8, 9 regions, but it self-intersects 3 times. So we should expect 1 plus 6 plus 3 for 7, but if they all intersect at the same point, it actually only creates a new region. It only creates 1 extra new region when we hit this intersection point. So really, the number of self-intersections, it's actually the number of distinct self-intersections, right, in this entire loop. So now that's out of the way, we know that, the diagonals of a pentagon do not self-intersect. So let's think about, well, how do we count the number of self-intersections? In this case, whenever we have, right, a path like this, let's think about how self-intersections can arise. They can arise whenever 2 lines, here and here, for example, intersect inside the circle. And, right, if they share a vertex like this, well, then they don't actually, they intersect, but they don't intersect within the circle, which is the condition that we need here. So actually the path doesn't self-intersect here. So basically we need the edges to be disjoint. They need to have different endpoints. So for example, right, we're drawing 5 edges. The 1, 2 edge, the 2, 3 edge, the 3, 4 edge, the 4, 5 edge, and the 5, 1 edge. These 2 cannot intersect inside the circle. Same with these 2, and these 2, and same with these 2. So really, how many possible pairs of these lines can intersect? Well, for example, 1, 2 can intersect with, and let's draw that here, 1, 2 can intersect with, or 3, 4, 5. Well, it can intersect with any edge that doesn't contain 1 and 2, right? So 3, 4, and 4, 5. Right, and we can see that every edge can self-intersect with a 2 other edges. So if we think about that, the total number of pairs that could possibly intersect is just 5 times 2. Notice that we divide by 2 because we're double counting each pair, right? 1, 5, 3, 2 would be the same as 3, 2, 1, 5. So you can see that there's 5 total pairs to consider. And now we just need to ask ourselves, given that, how often does this pair intersect, right? Because we can see that we can divide this question into using linearity of expectation, right? The expected value of a sum is always the sum of the expected values. We can just sum of the expected number, or the expected number of self-intersections each possible pair of 2 lines contributes. So for example, the expected number of self-intersections that the 1, 2 line and the 3, 4 line intersect, and there will be 4 other ones of these, right? So we can see that this will give us 0 if they don't self-intersect, or they don't intersect, and it will give us 1 when it doesn't, or when they do. And so therefore, this is just equivalent to the probability that 1 and 2 and 3 and 4 intersect. Right, so given 4 points, what's the probability that we draw 1, 2, and 3, 4, and they intersect? And we can see that this probability is symmetric for all 5 possible intersections. So really, this is just 5 times the probability that, for example, 1, 2, and 3, 4 intersect. Well, in this case, we can imagine, given or 1, 2 in this case, and 3, 4, we can think about drawing 1, 2, and 3, 4 in a different way. Instead of drawing the lines explicitly, we can see that we can fix the 4 points first, and then we can pick which vertices are 1 and 2 and which vertices are 3 and 4, right? Imagine we say that this vertex is 1, then we can see that in 2/3 of the cases, right, in this left branch and the right branch, we create an edge that won't intersect with the other edge. But in the other 1/3, right, if we choose the middle path there, that necessitates the need for another edge that passes through the center there. So you can see that in this case, this will produce an intersection if and only if, right, we choose one of the three edges that is a diagonal of basically this quadrilateral. See, we see that happens with a 1/3 probability, right? Imagine taking every possible way to connect two pairs of points in, among a set of 4. Then we end up with only 1/3 of them resulting in an intersection. So really this sum, which is just the expected number of self-intersections, is just 5 times 1/3, or 5/3. So our final answer, the expected number of pieces of our star, or the star divides the circle into, is just 6 plus 5/3, which equals 23/3. You can see the question asks for m plus n, so our answer is 26.